Neural networks, from biology to artificial intelligence. Hi everyone, and welcome back. Today, we're diving into one of the most fascinating areas of machine learning, neural networks. Have you ever wondered how machines can think or learn? Well, it all starts with an idea inspired by nature itself. Let's take a step back for a moment. Think about the human brain. It's made up of billions of tiny cells called neurons. These neurons communicate with each other through electrical signals, forming complex networks that allow us to process information, recognize patterns, and make decisions. Now, imagine if we could replicate this process in a computer. That's exactly what artificial neural networks aim to do. So, what does an artificial neuron look like? Picture it as a simple processing unit. It takes in multiple inputs, like pieces of data, and assigns a weight to each input, much like assigning importance scores. The neuron then adds up these weighted inputs and passes the result through an activation function, which decides whether the neuron should fire or contribute to the output. Now here, where things get interesting. A single neuron isn't very powerful on its own. But when you combine thousands or even millions of these neurons into layers, they form a network capable of solving incredibly complex problems. Think of it like building a house. One brick alone doesn't do much, but together they create something sturdy and functional. This brings us to the structure of neural networks. Typically, a neural network has three types of layers: an input layer, one or more hidden layers, and an output layer. The input layer takes in raw data, such as images or text. The hidden layers then process this data to extract features and patterns, and finally, the output layer provides the result, such as predicting whether an email is spam or not. Let me emphasize this. The magic happens in the hidden layers, where the network learns to identify meaningful patterns in the data. Depending on how you arrange these layers, you can create different types of neural networks suited for specific tasks. For example, convolutional neural networks, CNNs, are excellent for image recognition, while recurrent neural networks, RNNs, shine at understanding sequences, such as speech or text. So far, we've discussed the biological inspiration behind neural networks, the structure of an artificial neuron, and how neurons combine to form layers and networks. We've also touched on some common architectures and their applications. Does that make sense so far? Now, let's move on to an enhanced explanation of forward and backward propagation. Forward and backward propagation. All right, let's address the next big question. How do neural networks actually learn? It's a process similar to learning any new skill, like riding a bike. At first, you might be wobbly and make mistakes, but with practice and feedback, you improve. Neural networks learn in a similar way through two key processes: forward propagation and backward propagation. First up is forward propagation. Imagine you're feeding data into the network, such as showing it a picture of a cat. During the forward pass, the network takes this input, applies weights and activation functions, and processes it layer by layer until it produces an output. For example, predicting that the image contains a cat. Think of it as a journey. The input starts at the beginning of a path and travels through the network until it arrives at an answer. But here's the catch. The network's initial predictions are usually poor because the weights are randomly initialized. Reflect on this. If you were teaching a child to recognize animals, would you expect them to get it right on the first try? Probably not. They would need feedback to improve. Similarly, neural networks rely on feedback to adjust their weights and enhance performance over time. That's where loss functions come in. A loss function serves as a measuring tool, indicating how far the network's prediction deviates from what we ideally want. It measures the error between the predictions and the actual labels. For example, if the network predicts a dog instead of a cat, the loss function assigns a high error score. Understanding loss functions is crucial, as they guide the entire learning process. The goal of training is to minimize this error. Once we know how wrong the network is, we need a way to correct it. Enter backward propagation, or simply backpropagation. This process is akin to retracing your steps after a misstep on a bike, identifying where things went wrong and adjusting your strategy for the next attempt. During the backward pass, the network calculates how much each weight contributed to the error and adjusts them accordingly. It's like fine-tuning the strings of a guitar until you hit the perfect note. To perform these adjustments, we use optimization algorithms such as stochastic gradient descent, (SGD). SGD works by taking small steps in the direction that most reduces the error. Over many iterations, these incremental adjustments add up, enabling the network to make increasingly accurate predictions. In summary, during forward propagation, the network makes predictions, and a loss function measures the error of these predictions. Then, during backpropagation, the network updates its weights to reduce this error, guided by optimization algorithms like SGD. Activation functions. Now, let's focus on a critical component of neural networks: activation functions. You might wonder why we need these at all. Without activation functions, neural networks would essentially be fancy linear models, which have limited capabilities. They're like trying to draw a picture using only straight lines. No matter how many you use, you can hardly capture the curves of a face or the sweeps of a landscape. Activation functions are the secret sauce in a neural network. They add a critical twist by introducing non-linearity. Think of it this way. If you mix flour, sugar, and eggs in a bowl, you're performing a linear operation, simply combining the ingredients. But when you add heat, something magical happens as the mixture transforms into a delicious cake. Activation functions act like that heat by enabling the network to model complex relationships in data, much like capturing curves and dimensions in a drawing. There are several popular activation functions, each with its own strengths and character. For example, the sigmoid function squashes numbers between 0 and 1 and is often used when a probabilistic interpretation is needed, as in binary classification tasks. ReLU, rectified linear unit, operates like a simple gate, passing positive information while blocking negative values. ReLU is widely used in hidden layers because it helps the network train faster and avoids certain issues. Other options include TAN and softmax, the latter being used in the output layer for multi-class classification since it converts raw scores into probabilities. Have you ever wondered why we choose different activation functions for different layers? It's all about context. Each function has its unique advantages, and the right choice depends on the specific task and layer within your network. It is crucial to understand that activation functions allow neural networks to learn nonlinear patterns. Without them, even the deepest networks would struggle to solve complex real-world problems such as image recognition or language translation. The strategic combination and placement of activation functions can significantly enhance a network's learning and generalization capabilities. To summarize, activation functions introduce nonlinearity to neural networks, enabling them to model complex relationships. Popular choices include sigmoid, TAN, ReLU, and softmax, each suited to different scenarios. Deep learning frameworks. All right, we've covered the theoretical foundations of neural networks. But how do we build and train them in practice? That's where deep learning frameworks come in. Think of these frameworks as a workshop filled with power tools that provide everything you need to design, train, and deploy neural networks efficiently. Let's start with some of the most popular frameworks. You might have heard of TensorFlow, developed by Google, which is a powerhouse for building scalable models. Then there's PyTorch, created by Facebook, known for its flexibility and ease of use. And Keras, often running on top of TensorFlow, offers a user-friendly interface, especially for beginners. These platforms are like different brands of power tools available to a carpenter. Each has its strengths and caters to different preferences and use cases, yet all help you get the job done. These frameworks come with high-level APIs, meaning you don't have to write every detail from scratch. Instead, you can focus on designing your network architecture and tuning hyperparameters. It's like using pre-built Lego pieces instead of carving each block from raw wood. They simplify the process of designing and training your networks. But what about data? Neural networks are hungry. They need lots of high-quality data to learn effectively. Think of data as the raw materials needed for a construction project. Tools for data loading, pre-processing, and augmentation are essential. For example, you might resize images, normalize pixel values, or even flip and rotate images to create more training examples. It's like having a multi-purpose tool that not only builds but also prepares the materials. Another important aspect is visualization and debugging. Training a neural network can often feel like navigating a maze. Visualization tools help you track metrics like accuracy and loss, while debugging utilities allow you to inspect the inner workings of your model. Have you ever wondered how experts troubleshoot and improve their systems? These tools illuminate the process, allowing you to see inside your network, monitor its progress, and fine-tune its performance so that issues can be identified and addressed early. In summary, deep learning frameworks such as TensorFlow, PyTorch, and Keras simplify the process of building and training neural networks. In addition, tools for data handling, pre-processing, and visualization ensure a smooth workflow. Conclusion. And there you have it, a comprehensive overview of neural networks, from their biological inspiration to the practical tools for implementation. We've covered a lot of ground today, so please take a moment to reflect on what we've learned. Let's quickly recap the key points. We began by exploring the biological inspiration behind neural networks, understanding how artificial neurons mimic the workings of brain cells. We then examined the learning process, forward and backward propagation, and saw how the network refines its predictions, much like learning to ride a bike. We discussed the critical role of activation functions in introducing non-linearity, which is essential for modeling the complexities of real-world data. Finally, we delved into deep learning frameworks, the practical tools that transform theory into practice. Remember, mastering neural networks is a journey. Don't worry if some concepts feel overwhelming at first. With practice and patience, you will soon be building models capable of tackling real-world challenges. These core concepts lay a solid foundation for your journey into machine learning. Think of them as the building blocks that will help you create models capable of solving truly challenging problems. Thanks for joining me on this exploration of neural networks. I'm excited to see where your learning journey takes you next. In our next session, we'll delve deeper into advanced neural network architectures and explore how pre-trained models can further enhance your projects. Until then, keep questioning, keep exploring, and most importantly, enjoy this exciting journey into the world of AI and machine learning. Happy learning, everyone.